Okay, in this video I'm going to begin section 3.6, which is where we're going to look at the derivatives of the logarithmic functions. By the way, this will be the last section where we're going to be looking at differentiation rules. Okay, well, let's get right to it. Now, in algebra, we know that y equals log base a of x means x equal a to the y. Okay, that's the definition of a logarithm. I tell my algebra students, make sure that you know that. To me, that's the most important thing when it comes to working with logarithms. So I'm going to use this equation here, x equal a to the y. And now this equation is in implicit form, right? Since it has not been solved for y. So if I differentiate, it's more specifically, it's going to be implicit differentiation. And so the derivative of a to the y would be a to the y times the ln of a. But since we've differentiated with respect to y, we got to make sure that we complete the chain rule. We tack on a dy dx. Derivative of x is 1. Okay, and I'm solving for dy dx. So divide both sides by a to the y ln a. A to the y is x. And so I can get a formula here in terms of x. The derivative of log base a of x is 1 over x times the ln of a. Now, if the base of the logarithm is e, we're working with the natural logarithm, the ln of e is 1. Okay, so the derivative of the ln of x would be 1 over x. More times than not, you're going to be working with base e. Okay, so let's take a look at some examples. Suppose that we want to find the derivative of y equal the ln of x squared minus 6. Okay. Well, this would be a chain rule situation. The derivative of the ln of an expression is 1 over that expression, but then times the derivative of that expression. Okay, so 1 over x squared minus 6 times the derivative of x squared minus 6, that'd be 2x. And so we get 2x divided by x squared minus 6 is the answer. Here's another example. Y equal the ln of x cubed. Well, now that power of 3 is not inside the logarithm. Okay, so I can't bring that in front of the logarithm by using my laws of logarithms. The ln of x is inside of the cube function. So this would be a chain rule situation. I would begin differentiating as if it were just x cubed. Okay, bring down the power, reduce the power by 1. But then I got to complete the chain rule by differentiating the ln of x. Derivative of ln x is 1 over x, and so we get 3 ln of x, the quantity squared, all over x is the answer. Okay, here's another one. F of x equal ln of 4x minus 1 over the square root of x plus 3. So I've said that the derivative of the ln of an expression is 1 over that expression times the derivative of that expression. Okay, this would be a chain rule. And 1 over 4x minus 1 divided by the square root of x plus 3, I can flip the denominator there. So I have the square root of x plus 3 over 4x minus 1. Okay, and then I got to differentiate this guy here by using the quotient rule. Inside the quotient rule, I'm going to use the chain rule. Okay, so let me do that. We need the bottom, which is the square root of x plus 3 times the derivative of the top. Derivative of 4x minus 1 is 4. Minus the top, that's 4x minus 1, times the derivative of the bottom, that's where we're going to use the chain rule. X plus 3 to the 1/2, you're going to bring down the 1/2 power, reduce the power by 1, but then the derivative of x plus 3 would be 1, so I'm using the chain rule, but I'm just multiplying by 1, right? And this is all over the denominator squared. The square root of x plus 3 squared would be x plus 3. Okay, now let's see here. The next thing that I will do is I'm going to distribute the square root of x plus 3 into these terms in the numerator, and I'll distribute 4x minus 1 into the denominator there. Okay, and so here's the denominator, but the square root of x plus 3 times the square root of x plus 3, that would be x plus 3. I've still got the 4 in front. And then when you bring that into the second term, the square root of x plus 3 divided by the square root of x plus 3, those terms would cancel. So I'm going to have 1/2 times 4x minus 1. And if we distribute the 1/2 there, and also distribute the 4, You don't need to do this, but if you were to then multiply the top and the bottom by 2 so that you don't have a fraction, 2 times 2x is 4x, 2 times 25 over 2, the 2's cancel, so you get 25. We still have a 2 in the denominator. So this would be my answer in a complete simplified form. I would be okay if you leaving it in this form. There's really no reason to multiply the top and bottom by 2. But now there's another way that you could have done this. Okay, and that is you could have used your laws of logarithms to begin. We've seen several times that sometimes before we begin calculating a derivative, we want to simplify first and then differentiate. Okay, now I didn't do that here. I went right to the calculation of the derivative. And that's fine, okay, but what if I simplify by using my laws of logarithms first? I'm dividing the inner terms, and so that means that I can split this logarithm into 2. The operation would be subtraction, and I know that powers can come out of logarithms. So this power of 1/2 can come out of the second logarithm. Now what I've done here is no calculus, okay? There's no calculus. I mean, this is just simplifying logarithms using what I know from algebra. Now let me differentiate. Okay, the derivative of the ln of an expression is 1 over the expression times the derivative of the expression. So I'm going to say 1 over 4x minus 1 times the derivative of 4x minus 1, that's 4, minus 1/2 times derivative of ln of x plus 3, that'd be 1 over x plus 3 times the derivative of x plus 3 is 1. Okay, now if you were to simplify this by cross-multiplying and then combine your like terms in the numerator, you would get exactly what I had circled up here. Now, this method would be probably a little bit quicker, okay, and so I would say that, when working with logarithms, consider using your laws of logarithms first before you differentiate, okay. Now, not always will that be the case, but it can sometimes make the problem easier than just going right to the derivative. This was an okay option, but I had you have to start by using the chain rule, and you've got a quotient rule, and then within the quotient rule you got another chain rule. Okay, so it's very easy to slip up on, especially the simplification part, all right, now how about this one? What if we had y equal log of 2 plus sine x? So whenever the base is not base e, we need to make sure that we multiply the denominator by ln of a, whatever that base is. So here I have base 10, right? And I'm going to start by, this will be a chain rule, 1 over 2 plus sine x times ln 10, and then times the derivative of 2 plus sine x is cosine x. So cosine x divided by ln 10 times the quantity 2 plus sine x, that would be my answer. Okay, here's another one, another chain rule. Okay, if we want to find g prime of x, we're going to have 1 over x to the 4th plus 3x plus pi times the ln of 3, since the base is 3, and then finish the chain rule by multiplying by the derivative of x to the 4 plus 3x plus pi, that'd be 4x cubed plus 3. A mistake that I will see a lot from a student is that they will forget to multiply the denominator by the ln of a. Maybe it's because so many of the problems are where you have base e, and they forget about that. But don't forget about that. I mean, really I'm multiplying the denominator by the ln of e, but the ln of e is 1. I just, we don't usually write times 1. Okay. Here's another one. Y equal the ln of cosine x. Okay, well that'd be another chain rule. So 1 over the expression times the derivative of the expression. I got 1 over cosine x times the derivative of cosine x, that's negative sine x. Sine x over cosine x is tangent x. Negative tan x is my answer then. There's a theorem next. It says that the derivative of the ln of the absolute value of x is 1 over x. Okay, now we'll need to use this later on once we get to some things in chapter 5. So just maybe make a mental note of that. But basically, the absolute value bars are not going to matter. You're going to still differentiate as if they were not there. course, I can't take log of a negative, right? And x can't be 0. And I know it can't divide by 0. Also, ln 0 is undefined. Okay, now a proof of this, if x is positive, we've done that already, right? That's what I have shown right here in this calculation. Okay, ln e is 1. Now, what if x is a negative? Well, the absolute value of x would be the opposite of x if x is a negative. Like if I ask you the absolute value of negative 6, I get the opposite of negative 6, which would be positive 6. Okay, so I'll use that here. The derivative of the ln of the absolute value of x would be the derivative of the ln of negative x, okay, since we're assuming x is negative, and you use the chain rule. So the derivative of the ln of an expression is 1 over the expression times the derivative of the expression. Derivative of a negative x is negative 1. The negatives cancel there, and so you still get 1 over x. All right, so here's an example. Suppose I want to find the derivative of the ln of the absolute value of secant x plus tangent x. Well, I'm going to handle that just as if the absolute value bars aren't even there, right? It's 1 over the expression times the derivative of the expression. So 1 over secant x plus tangent x times the derivative of secant x plus tangent x. Derivative of secant x is secant x plus tangent x, plus derivative of tan x, that's secant squared x. Simplify that. Secant x is in common to these two terms in the numerator. You can factor that out. And that will allow you to cancel these two expressions here and leave you with just secant x. Okay, now the last thing I want to talk about in this section is logarithmic differentiation. We were looking at derivatives of logarithmic functions. Logarithmic differentiation sounds very similar, but it's actually a different sort of calculation. What we mean by logarithmic differentiation is that you could have an expression that had nothing to do with logarithms in it, but you're going to incorporate logarithms into the calculation when you differentiate. We call that logarithmic differentiation. Okay, so like here's an example. Suppose that I want to find the derivative of y. Well, if I were to go right to the derivative calculation, I would have a quotient rule, and within the quotient rule, I would need to use the chain rule twice along with the product rule. That doesn't sound like tons of fun. It sounds like something that I could easily slip up on, especially with the simplifying part. Okay, so logarithmic differentiation might be maybe a better option to consider here. So now I didn't have any logarithms to begin with, but I'm going to go ahead and take the ln of both sides. And now I can use my laws of logarithms. So if you're dividing the inner terms, that means that you're going to subtract logarithms. And if you're multiplying the inner terms, that you're going to be adding logarithms together. Okay, and we know powers can come out of logarithms, right? So I can pull out the power of 7/4, the power of 1/3, the power of 13. Okay, now I have an equation here that is an implicit form, so if I want to differentiate, I need to use implicit differentiation next. Derivative of ln y would be 1 over y, but then because that's in terms of y, I need to finish the chain rule. I need to multiply this by dy dx. On the right, all this is in terms of x. You differentiate x as usual. So you're going to have 7/4 times the derivative of ln of x is 1 over x, plus 1/3 times the derivative of ln 1 minus x squared, that'd be a chain rule. You have 1 over 1 minus x squared times the derivative of 1 minus x squared, that is negative 2x. And then minus 13 times the derivative of ln 9x plus 2, that'd be 1 over 9x plus 2 times the derivative of 9x plus 2 is 9. I need dy dx to be all alone, so I'm going to multiply both sides by y. All right, and also I'm going to simplify this a little bit here. I got 7 over 4x minus 2x over 3 minus 3x squared, and then minus 13 times 9 is 117, divided by 9x plus 2. The last thing is you'll replace y with this expression here is in terms of x. That way everything is in terms of x. So here would be my answer for dy dx. Okay. Now, this method might be, a better plan rather than, going right to a derivative. Because like I said, if I were to immediately go right to y prime, I would be using the quotient rule, and then inside of that I would have the chain rule twice along with the product rule. Okay, and so it's very easy to make a mistake on probably something like that. But I did have, so when we have the option to use logarithmic differentiation, that's an option. Now sometimes it's our only option. Okay, so here's an example of what I mean by that. Suppose that we want to find an equation of the tangent line to the graph of y equal x to the power sine x at the point pi over 2, pi over 2. By the way, this point would be on the graph of this curve, whatever this curve looks like. If x is pi over 2, sine pi over 2 is 1. Pi over 2 to the first is pi over 2. That'd be my y value. Okay, now I can't use a power rule, okay, because I've got an expression involving x in the power. The only time that you can use the power rule is when you have a constant in the power. I can't use anything about exponentials also because the base is x, right? An exponential is where the base is a number, not some variable that's going to change. So my only option here is to use logarithmic differentiation. Let's go ahead and take the ln of both sides. That will allow me to bring the power in front of the logarithm there on the right. And now I'm going to take the derivative of both sides. I'm using implicit differentiation. So the derivative of ln y would be 1 over y, and then times dy dx. On the right, I need to use the product rule. So the first is sine x times the derivative of the second. Derivative of ln x is 1 over x. Plus the second is ln x times the derivative of the first. Derivative of sine x is cosine x. Next, you're going to get dy dx all alone by multiplying both sides by y. Y is x to the power sine x. And now I've got a formula in terms of x representing the derivative. I would like to know the slope of the graph when x is pi over 2. So I'll go ahead and plug pi over 2 into the derivative here. Pi over 2 to the power sine pi over 2. Sine pi over 2 is 1. So pi over 2 to the first, that'd be pi over 2. Inside the bracket, sine pi over 2 is 1. Divided by pi over 2, 1 divided by pi over 2, that'd be 2 over pi. Plus ln pi over 2 times cosine pi over 2 is 0. Okay, so that's going to knock out this term here since I'm multiplying by 0. Pi over 2 times 2 over pi, that'd be 1. So the slope of the graph at this point is 1. Now I can use my point slope formula to find the equation of the tangent line. Y minus y1 is pi over 2 times the slope we just said is 1 times the quantity x minus x1 is pi over 2. If you add pi over 2 to both sides, you get y equal x. So y equal x would be the equation of the tangent line to this graph at the point pi over 2, pi over 2. Now, I mentioned early on in this problem, logarithmic differentiation is my only option. There is no other way to find y prime in a problem like this. In general, whenever you have a function to a power that is also a function, and both of those functions involve x, like what you see here, logarithmic differentiation is your only option. Okay, a function to a function power, you consider using logarithmic differentiation. All right, that's all there is in this section. So the homework is on page 223. Be sure to look at the problems there.